Hi and welcome to Brokabi Anthrax. So again today we are going to solve a couple of questions to understand some concepts on strength of materials. Right, so here the first question is a two-story column ABC in a building is constructed with hollow square section as shown in the given below. Right, so the rooftop is loaded with 80 kilonewton and the floor at the midsection is loaded a load of 100 kilonewton. Obtain the compressive stresses at the two sections XS and YY. Okay, so we have to find out the stress here and the stress here. Right, simply straightforward question. First of all, let me calculate the cross-sectional area here. So the area would be equal to the cross-section, the hollow column, right? So which is nothing but 200 into 200 minus. So here we are going to have to subtract 15 and 15 here meaning 30. 200 minus 30, we are going to have 170 into 170. So the answer here is going to be 11100 millimeter square. Note that this is in millimeter, right? So this is going to be our area. I'm going to keep my answers in Newton per millimeter square, right? So in XX, so the only load that has been acting in XX will be P1. So let me give this as AB, right? So I'm gonna have or let's say I'll name this as point A, this as point B, and this as point C. So in the portion AB, so it is nothing but in AB portion, so the stress, I'm going to have sigma AB as the compressive force. Let me just give as the name same. The load will be P1 divided by the area as A. So the P1 is nothing but 80 into 10 to the power of 3 divided by 11100. So which is nothing but 7.21 Newton per mm square. Right. So again in YY section, so which is nothing but in AC, meaning the whole of the column, right? So we are going to have the total load is going to be P1 plus P2, which is nothing but 180 kilonewton, right? So here sigma AC, which is nothing but the entire column, we are going to have P by A. The P is nothing but 180 into 10 to the power of 3 divided by A is 11100, that is nothing but 16.21 Newton per mm square. So this is going to be the total compressive stress in the entire column, right? So moving to the second example, a bearing pad consisting of a flexible material of thickness 10 mm capped by a thin plate of dimension 50 into 750 cross 75 millimeter square is subjected to a horizontal shear force of 5 kilonewton. Determine the average shear stress. A straightforward problem, so we are going to have to calculate the tau average, which is nothing but the shear force divided by the shearing area, so which is nothing but the shear force they have given us 5 into 10 to the power of 3 divided by the area is going to be 50 into 75, so which is nothing but again 1.33 Newton per mm square. Right, so here let me just brief of the different stresses that a material can be added, or different types of stresses. Right, so the first one is going to be what? Normal stress. Right, so in normal stress we have two types of normal stress. One what we call as a direct stress or principal stress, so other is going to be a bending stress. Right, so this is going to be because of force which passes through forces at CG. Let me say best example is going to be a block. This is going to be a direct stress, right? So a bending stress. So here apart from CG, let's say if I have a beam something like this which has been supported at two ends, a simply supported beam. Let me have a force P somewhere here, let's say, right? So I'll consider a cross section. Let me tell it as A and B. So in this particular cross section I'm gonna have a different kind of loading of this particular stress. So in this direct stress or principal stress, at a cross section, let me just go with this AA. So in the cross section AA, the tensile forces are going to be uniform, or the tensile stress is going to be uniform, but that won't be the case in the bending stress. In the bending stress, we are going to have a neutral axis at the center, usually, depending upon the cross-sectional area, obviously. So here, for this particular setup, I'm going to have the first half is going to be compressive, second half is going to be the tensile. Right, so this part is going to be the tensile part, and this part is going to be compressive part. Right, so again, the second type of force or the stress is nothing but shear stress. Right, so in shear stress, so obviously again we have two types of shear stress. We have direct shear and we have something called as torsional shear. Right, so this is because of the direct shear force which has been acting on the surface. So this torsional shear force is due to torque applied for a particular rotating element or torsion. All right, so let me just also give you the sign convention that we're going to use. So if I have a block something like this, so for positive, the top of this is going to be towards the RHS, the bottom is going to be towards the LHS, and the right portion is going to will be towards the upward, and the left one is going to be towards downwards. So this whatever the direction, if the shear force in this particular directions, we are going to consider that as positive, and the opposite is going to be true for the negative. In negative, the upward surface or upward plane is going to be towards LHS and vice versa. Alright, so this is going to be our sign convention. Alright, so with this, all of these knowledge, let me move to the next question. Let me talk about the next one. A round bar of length 1.5 meter is loaded in tension as shown in figure. Okay, the normal strain is 2 into 10 to the power of minus 3 is measured by a strain gauge. What elongation of the entire bar, so small spelling mistake, bar can be expected at this load? Okay, as simple as a very straightforward question. So we are going to have epsilon is equal to delta L by L. Right, so simple formula, delta L is going to be, I don't know, I have to find the delta L. I'll keep it in LHS. So here epsilon is 2 into 10 to the power of minus 3, and L is going to be, I'll keep this delta L is millimeter, so I'm going to have 1.5 into 10 to the power of 3, so which is nothing but 2 into 1.5 is 3 mm. So delta L of this particular element, or let's say a bar, is going to be 3 mm. Okay, straightforward question. Let me move to the next one. Right, so here we'll have to talk about stress tensors. Right, so let me just give you some input regarding the stress tensor, and then we'll come back to the initial problem. Okay, I'll just leave some space for this, and then I'll talk about the stress tensors. Okay, stress or strain can be expressed in a tensor form, right, or a matrix form. Right, so first I'll write a stress tensor, and then I'll go for the strain tensor. So for the stress tensor, for a 3D diagram or a 3D block, let me just draw a simple block here. Right, right, so let me consider this as X, this as Y, and this as Z direction. So here we are going to have in the plane YZ, in the plane, sorry, XY plane. So firstly we are going to have some direct stresses, so this is going to be sigma xx, and also I'm going to have some shear. I'll take the positive shear direction, so remember the right face will be upwards, and this guy, so here, so this quantity is going to be tau x y, and this is going to be tau xz. Similarly here, firstly I'll have the direct stress, which is going to be sigma z, and upward direction I'm going to have tau zy, and towards the x direction again I'm going to have tau zx. Similarly in the y direct stress, sigma y, towards x direction tau yx and tau yz. So these are going to be, I've just written this for three phases. Again in the opposite three phases, again I'm going to have a similar stress forces, right? So if I just consider these three, we'll have a stress matrix something like this. So sigma xx and tau xy and tau xz and tau yx, sigma yy and tau yz, and then tau zx, tau zy and sigma zz. Right, so coming to the strain, so this is going to be stress. Coming to the strain, the tensor is going to be, firstly I'm going to have the direct strain is going to be represented by epsilon, the shear strain is going to be represented by phi. Okay, so epsilon xx and phi xy divided by 2, and phi xz divided by 2, phi yx divided by 2, epsilon yy and phi yz divided by 2, and again phi zx by 2, phi zy by 2, and epsilon zz. So this is going to be our strain tensor, right? So here a point to note is, in both x and y we are going to have tau xy is going to be tau yx, and for all the other directions as well, even in this shear, so we are going to have sigma xy, sorry, phi xy is going to be phi yx, right? So this is going to be a symmetric matrix. So right, for a total shear strain, let's say total shear strain, let me tell this in, let me go with xy plane. So in the xy plane I'm going to have phi xy by 2 plus phi yx by 2, so this is going to be phi xy, right? So this is going to be the total strain in xy plane, similarly for the other planes as well. So with this knowledge, let me come back to my question. So they have given the strain matrix or strain tensor. Let me just equate this to our known strain matrix, so which is nothing but epsilon xx phi xy by 2 and phi xz by 2. So I'll just go with the first row. So here they have asked me to calculate the shear modulus of the test block, right? So for the shear modulus I'm going to go with the xy plane. Any plane, I can go with any plane. Let me just make my life easier, I'll go with only the xy plane, right? So here sigma, sorry, phi xy has given as 0. Divided by 2 is given as 0.005, so which means that phi xy is equal to 0.01, right? So the total shear modulus G is given by shear stress divided by shear strain, so which is nothing but the shear stress that they have given as applied as 1000 megapascal. So here 1000 into mega is 10 to the power of 6 pascal divided by the shear strain, which is nothing but 0.01, so which gives me the shear modulus as 100 into 10 to the power of 9 pascals, which is nothing but 100 into 10 to the power of 100 gigapascal. 10 to the power of 9 is giga, so the option B would be the right answer, Right, so moving to the next question. So right, so here we have the displacement of a particular point in x and y direction. So they have asked me to calculate the xy stress. Okay, so the shear stress and the direct stresses can be represented with the help of displacement equations, right? So what we call as a differential form of strain. So let me just leave some space here and let me write down all the formulas involved, or I'll write the formulas involved and then solve the problem. Right, so sigma epsilon xx is going to be del u by del x. So epsilon yy is going to be del v by del y, and epsilon zz is going to be del w by del z. Right, and phi xy is going to be del u by del y plus del v by del x, and epsilon yz is going to be del v by del z plus del w divided by del y, and phi xz is going to be del u by del z plus del w by del x. Okay, so applying these formulas here, so we only want the xy plane, so I'll going to only use these things. Right, so here in the xy plane, the total shear stress in one particular plane, that is sigma xy, is going to be del u by del y plus, so this particular formula, I'll just apply the u and v here. Del by del y is equal to minus 3x plus 7y into 10 to the power of minus 3 plus del by del x of minus 2x plus 5y into 10 to the power of minus 3. Right, upon simplification, so let me just differentiate this. So this is going to be 0, so we are going to have plus 7 into 10 to the power of minus 3, so this is going to be 0, so we are going to have minus 2 into 10 to the power of minus 3, so which is nothing but 5 into 10 to the power of minus 3. So this is going to be our shear strain in the xy plane. They've asked me to calculate the shear stress here. So the shear stress is going to be in the xy plane is going to be g into phi xy, so which is nothing but g is given as 100 gigapascal, that is 100 into 10 to the power of 9 into the sigma value, phi value, which is 5 into 10 to the power of minus 3, so which is nothing but 500 into 10 to the power of 10 to the power of 6, so which is nothing but 500 megapascal. Right, so the correct answer would be option D. Okay, this would be the end of this video. See you in the later videos. Happy learning. Take care. Bye bye.